All right. So today is the last regular question and answer session, except for the one after Easter, where we will discuss the solutions for the example exam. The example exam is online on the webpage, so you can download it. And after going through this set of slides, we'll quickly go through the questions in the example exam too. So today, we're really quickly going through the whole semester of operating systems and really discussing the most important things you definitely need to know for the exam. Of course, this is the minimum amount you need to know for the exam. Knowing more is always better, as you should know. So, semester review, here's my mouse. What's relevant? So, of course, the most urgent question from your side is like, what can I completely ignore for the exam? I mean, it's a mandatory course, so if you're not interested in some of that stuff, that's perfectly all right. So, and if you ask most of the lecturers, they will tell you everything's important. Well, everything's important, yes, except we're taking out some stuff to make it a bit easier for you. We're taking out lecture 8 from source code to process. So you don't need to know all the details about ELF files, about linking and symbol tables and stuff like that. They are very useful to know for your future career, obviously, when you want to develop software, but we're not going to ask you details about this in the exam. We'll also take out lecture 13 from the exam. That's a lecture about real-time scheduling. So real-time scheduling, you've seen, and you've seen some of the exercises. This can be quite demanding, getting it right. It makes for a nice set of exam questions, but to be honest, this should be part of a separate course. So we included it here for completeness, but well, I'll make life a bit easier for you, so you don't have to learn all these details about real-time scheduling. But note that the general scheduling, so lecture 12, is very relevant for this exam. So regular scheduling and operating system is, of course, one of the central topics. Real-time scheduling is also an important topic, but not for the exam. We're also taking out lectures 19 and 20, the embedded systems part 1 and 2 lectures about embedded systems, real-time operating systems from Dortmund, so the lectures by my former boss. And we'll obviously also take out lecture 22 because that was an external lecture, so the second security lecture. So everything else is and can be and will be of relevance for the exam. Obviously, we won't be able to cover every topic and questions in the exam because there's only so much time, but there will be a selection. In addition to the lecture materials, what's also relevant? Obviously, the theoretical exercises. So the materials from the lectures as rehearsed in the theoretical exercises, because, yeah, obviously the questions in the exam might be similar to some of the questions in the theoretical exercises, but also practical exercises. So we expect you to have worked on the practical exercises on your own or in a group, but you've contributed to this. So essentially, we might ask questions about contents like of what a shell might do. And this is much easier to answer if you implemented the shell yourself or if you participated in the implementation. What about the things early on? So the C crash course. Well, the exam will certainly require to have knowledge of C on an advanced level. So on the level you need to do the exercises here, but we won't ask specific questions about details of C programming. So you've seen these theoretical exercises about like preprocessor magic and stuff like that. We won't go deep into that, but of course you have to be able to read and also write C code and to understand C code, and also to be able to find and fix errors in a given piece of code. What about Unix? Well, we demonstrated operating systems concept using Unix system calls, libc functionality. So you should know the basic set of system calls, for example, to handle files and so on. This was fundamental for the practical exercises. So this is obviously also fundamental here. I will not go to ask you specific details of given Unix or Linux implementation. So how things are realized in macOS or Linux, with one exception, perhaps like different file systems. So we've seen different file systems like Fat file system, Berkeley file system, the traditional Unix file system, and so on. So this might be the case, but these are general types of operating systems, which by coincidence are standard in one or the other operating system. So for Linux, you can choose between so many different file systems. So these might be relevant. Okay. So in the rest of this slide set, I will give you a quick walkthrough summary of the most relevant topics we discussed in this course. And this is, I think, the absolute minimum knowledge of areas I expect you to have knowledge about, but it's certainly not exhaustive. So yeah, more details are better. And yeah, let's see what we can do. So introduction to operating systems. And you see I'm asking typical questions here, which you might want to use to think about, to go through the material again, try to find the answers. These are basic concepts. So we talked about an introduction to operating systems. So how did they start? What was the history? And important questions here would be like, why were operating systems actually developed in the beginning? Why do we need them? How did the features of operating systems evolve? And what did it have to do with the development of available hardware? So you could imagine that something like virtual memory availability and the availability of memory management units, so the feature in the OS and the feature in the CPU had to be evolved together, for example. And also, how do we define an operating system today? I do not expect you to know details about the historical computers and historical operating systems discussed in that lecture. I think this is very interesting, but it's not relevant for the exam. So the first real important content was about resources and computer architecture. So we talked about the interaction of computer architecture and an operating system. We talked about what a resource is, how to manage resources, and what the operating system has to do with it. So I expect you to have like a general knowledge of computer architecture. So you should know what a CPU is, what a RAM is, what a character and a block IO device is, what a bus is. So in general, the building blocks of a computer system, how they interact. And of course, if you have the building blocks, which resources are represented by these building blocks. So you should, for example, know a disk is a block device in an operating system, or a terminal or a printer might be a character device. You should know a bit about the device handling, so device drivers. So how does the code in an operating system interact with hardware resources? So you should know about things like port and memory mapped IO. You should know about interrupts as an asynchronous notification. You should know that there is a mechanism called DMA, which doesn't use the CPU to transfer data. And you should also think about what are the most relevant developments in computer architecture of the last decades. So what really makes up a computer today, and which problems and which benefits come from these developments. So computer architecture obviously is important. You don't need to know it in detail. I'm not going to ask you like about cache coherence stuff, which would be part of computer architecture lecture. You should, but for example, know what a TLB is when we discuss virtual memory. So it's a bit of a high level knowledge of computer architecture without going into too many details. But of course, this is required because an operating system interacts directly with the hardware. So yeah, some fundamental knowledge here, I think, is appropriate. Then we talked about challenges and tasks of operating systems. So we discussed abstractions provided by an operating system. So why do we need abstractions? What do these abstractions look like? And we talked about the tasks an operating system has to perform to provide abstractions, to provide functionality to applications. And we talked, of course, about the resulting problems and challenges for an operating system. So you should know which abstractions a modern operating system provides. So CPUs or processors or memories or file systems or security. So these abstractions are some concept on higher level. So above the hardware, that's not directly visible on hardware level. So for example, you have virtual CPUs because you do preemptive multitasking. That might be an example. And then you can model it further on by processes, which include a share of CPU and a share of memory. You can have virtual memory as an abstraction. You can have file system as an abstraction over block devices. You can have the concept of a user and security, for example, and access rights, which are not direct hardware concepts, but which just is part of your operating system implementation. And of course, the thing we started off is actually defining what a process is. So you should know the difference between a program and a process. You should know how processes can interact with each other and with the operating system. So things like system calls, but also synchronization and deadlocks especially. You should know about the different views of processes, why they exist. And you should know about the states of a process and what characterizes the states. And of course, how to switch between these states, which transitions between states are legal, which transitions between states are not possible in an operating system. So one standard way here is would be a question of why is it not a good idea to allow a process to directly return from busy or blocked to running state? That would be the typical stuff, like why is there this asymmetry in our very, very simple process state diagram? And then we talked about processes a little more, about the abstraction that process provides. We've already seen the definition of a process, the difference to a program. So a process is a program in execution. So the program is what you compile and link, what's sitting on your hard disk or somewhere. And when you start it, you load this program into memory and you add it with runtime state, like the contents of your heap and your stack to give a moment, the program counter, register contents, open files, other allocated resources, and so on. We've talked about process hierarchies in Unix, and you should know what it is and why we have it. So you should know about parent and child processes. You should also know about these special cases like orphan processes. You should know what a zombie is in terms of operating systems. And you should also know about the very special meaning of process one, the init process in Unix. You should also know how processes can perform I/O, how this can be configured, how this is related to this Unix philosophy of doing one thing well, and the Unix philosophy of everything is a file. I already mentioned system calls. So how can a process actually request a service from the operating system? So you can't just jump into an arbitrary location in the kernel. You have to use a special gate to get into the kernel, and that's what a system call does. And then we talked about how to create, control, and terminate processes. So we had fork and exec, we had kill, and several other calls. So which Unix syscalls are used for process management. And we've also discussed the pros and cons of the Unix fork and exec model. You should also know a bit about optimizations that are done in Unix for process creation. So fork uses in most implementations a special copy on write model. You should know why it is done, what the interaction is, what does it actually optimize. And then, of course, we started out with a simple three-state model of ready, running, and blocked processes. And we've seen extended process state models. So you should at least know a bit about the details of this extended model, though it can be very complex. The most complex we've shown, you don't need to know every detail about that. And by the way, it's a home exam, so you can look it up anyways. And we've also talked about threads, and threads were causing lots of fun when implementing your web server, I guess. So you should know about why we introduced threads in Unix. So why is the overhead of a Unix process relatively high? Why is it relatively costly to create a Unix process, even with copy on write? You should know about the concept of an address space, and you should know how address space, this concept, differs between processes and threads. You should know about the basic thread models in Unix, so pthreads, and the Windows models. So essentially that in Unix, originally you didn't have threads, you only had processes, so threads came later, whereas Windows is a more recent development, so they could start building threads in from the very beginning. We've also talked about what we call fibers, so user level threads, and you should be able to consider the pros and cons of threads versus fibers and know the difference between them. And we've also talked about cooperative multi-threading. So the ideas behind what we showed, Duff's device and the proto threads, you don't need to know the details of their implementation, but the general idea and of course the difference between cooperative multitasking or multi-threading and the preemptive way, that's important to know. Then we talk quite a bit about concurrency. So how do I actually get a set of processes to interact? So we've talked about mutual exclusion and synchronization, the interaction of parallel activities, and the problems and possible solutions. So you should know about what shared data or shared memory communication is, why it is problematic. You should be able to give an example of a situation that can cause a problem. So a race condition, for example. You should be able to understand multi-threaded code, like using p-threads that use shared data. You should be able to explain what a race condition is and give an example. You should probably ask yourself, why are these actually so hard to detect and debug? Then, of course, you should know what synchronization is, what it is used for, which different options you have, like semaphores and mutexes and monitors. One very central term here is critical section. So you should be able to define the term critical section. And then, of course, we have logs. You should be able to define what a log is and how it's used. And you should also know a bit about the implementation of logs. So you should know about all these details we talked about, like atomic operations, suppressing interrupts, using semaphores here. And then, of course, you should know what a semaphore is, which operations you can use on these. And you should also be able to define the implementation of a semaphore, or the other way around, if the implementation of the semaphore is given, and that's something I love to do, like giving some code which has a bug, like this is a code that should implement a semaphore. There's a problem. Can you describe what the problem is? Can you propose a fix to this? And of course, we've discussed problems like the reader-writer problem, solved using semaphores. We've also discussed the dining philosopher's problem. So you should be able to understand and describe these. And finally, we discussed monitors. So you should be able to at least know a bit about monitors and what the difference to semaphores is. Then we talked about further problems with concurrency, so deadlocks and starvation, so the problems that show up and how we can solve this. So here we have central terms, deadlock and lifelock. So you should be able to define the terms and explain, give examples, for example, for situations leading to deadlocks or lifelocks. You should know about these three necessary conditions for deadlocks to occur, and you should also know about the fourth additional condition, that's a required condition. So we definitely have a deadlock. You should, of course, also know about the process dependency or resource allocation graph here. So which types of resources you actually have for synchronization, how are they modeled in a resource allocation graph? How do you construct it? And of course, then how can you detect the deadlock in this graph? And maybe also think about why this is not very practical to do in a real system with thousands of processes and hundreds of thousands of resources. The dining philosopher's problem I already mentioned. So why can deadlocks occur here? You should be able to answer that question. You should be able to describe a solution, and maybe also, that's a bit advanced, discuss the efficiency of different solutions to the dining philosopher problem. Then finally, you should be able to explain how you could prevent deadlocks, and also the safe, unsafe states we discussed there, and also methods to resolve deadlocks, and discuss the pros and cons of these. So this is very fundamental, deep operating system topic that's part of every operating system course. We're always talking about concurrency in operating systems, obviously. Lecture 8 is not part of the exam, so from source code to process, we've discussed all the details here about help files and the tasks of the tools. I'm not going into details here, but these might be useful if you develop software on Linux, Unix, or even on Windows later on. But you can ignore lecture 8 for the exam. Memory management is something you cannot ignore, and that's one of the other important resources we're going to manage. So what are the requirements for memory management if you have a multi-programming system? So you have several tasks running at once. We had discussed policies and strategies of memory management. We have discussed the basic problem of memory allocation. So we had discussed things like fragmentation, for example. Then you should be able to describe how dynamic memory allocation works. You should be able to describe the different approaches and to discuss their pros and cons. Different placement strategies are important. And of course, then fragmentation, as already mentioned, we have internal and external fragmentation. You should be able to define both and discuss their properties, and also discuss where different allocation methods are typically used. And finally, you should also be able to describe differences between swapping, segmentation, paging. You should be able to explain how paging as an operating system concept interacts with the MMU, with the TLB, with the page tables that sit somewhere in memory, and also how you can optimize this using hardware or software approaches like a TLB, as I mentioned, for example. Then, of course, based on this, we discussed virtual memory. So we discussed the locality principle in computers. So we have spatial and temporal locality, and we discussed how locality can be used to optimize performance. And then we discussed the idea behind virtual memory, which was, of course, already started in lecture 9. So we discussed the abstraction or illusion created by virtual memory, that every process that's running has the whole memory of the whole computer for itself. Whereas in reality, of course, the physical memory is shared between all the processes running at the same time. You should know how demand paging works, so what a page fault is, what happens when a page fault occurs, what the OS does, and on the other hand, what the hardware does when page faults are handled. And then we discussed page replacement strategies. So if your memory is full and we need to load in a site from a page from our swap space, which different algorithms can we use to replace one page in memory with the page just freshly coming in? So we've seen different strategies like FIFO, optimal, LIU, and second chance. You should know about the different page replacement strategies and also discuss their pros and cons, and also be able to simulate different strategies. If you have an access sequence, and you see this in the example XM, then you should actually give for each subsequent page request, you should give the set of pages currently in memory, and you should tell which page is going to replace for which strategy. Finally, we discussed thrashing. So you should be able to define this and name causes and possible solutions. And you should also know what the working set of a process is. And you should ask yourself, how can you actually determine it? So we talked about CPUs and memories, and we also talked about synchronization a bit. And so here we went a bit into more details in lecture 11 on inter-process communication. So you should know which approaches to IPC exist and give their pros and cons. So shared memory versus message-based. You should know about primitives for message-based communication, synchronization methods, how to address processes, the IPC methods in Unix. And you should know at least a bit about signals, pipes, so named and unnamed pipes, message queues, and if you all used sockets, obviously, in the web server example. And you should also know what RPC is and how it relates to IPC. Yeah, we also discussed scheduling, obviously, so processors and processor time as a resource. So you should be able to define the terms dispatching and scheduling. You should know which dispatch states exist, which level of scheduling they're related to. You should be able to know what short, medium, and long-term scheduling is. You should be able to describe the process state transitions related to scheduling levels. Excuse me. You should be able to define what preemptive scheduling is. Compare it to cooperative scheduling. You should be able to define the advantages of preemptive scheduling and also the mechanisms required to implement preemptive scheduling. And then you should be able to give examples for scheduling strategies, different ones, explain how they work. You should be able to determine scheduling orders for a given strategy and also discuss pros and cons of the different strategies and evaluate them. We also talked about multi-level scheduling, how this is related to priorities. And sorry, we talked about scheduling strategies in Unix and Windows. Then we talked about I/O management and disk scheduling. So how do devices and the OS interact? Different methods, classes of devices, so character block devices and maybe special other devices. Interrupts and DMA, how to address I/O devices, so memory map versus special I/O commands. We discussed what a device driver is, how it interacts with the hardware, the tasks of the OS related to devices, and also the representation and abstraction of devices in Unix. So we have character devices, we have block devices, we have other devices. You should be able to name the property. For example, on a block device, you can seek to every location of the block device from the start to the end, whereas on a character device, you just get a stream of characters, and it's impossible usually to rewind on that stream of characters to a previous input. Yeah, how can we use devices and user processes? So the usual set of system calls: open, read, write, close, and so on. The related syscalls or libc functions. We discussed buffering and why this is important. And in this context, we described a ring buffer. And of course, you were supposed to use a ring buffer in the web server example. So you should be able to explain how a ring buffer works, where it's typically used, and I guess also essentially to get the implementation. Sorry, I've just seen the request on the other screen that somebody required transcription. Now it's enabled. Sorry for not seeing this earlier. And finally, we talked about disks. So how does I/O scheduling for disk drive work? So how do we make it efficient? Of course, for a physical hard disk with a real rotating rust, as we call it. So just magnetic disks where you really have mechanical components like an arm and a rotating motor. This is not as relevant for modern SSDs. Then we talked about file systems. We had 2 lectures about this. So you should know what the file abstraction is, why this is useful, the syscalls and libc functions in Unix to handle files. You should know what a virtual file system is. You should know what mounting, unmounting of a file system means, what the effect of this on the Unix directory hierarchy is. You should know about methods to map a file to disk blocks, to manage free space. We've looked at the different free space managements, and also the directory and inode structures for typical file systems like Unix system file for BSD or Linux, for example. And then we also talked about modern file systems. So we talked about challenges for file systems, reliability of disk storage, like we talked about RAID arrays, for example. We talked about the buffer cache, logical volume management, RAID levels, and then finally, we also talked about journaling and log structured file systems. So how do they work? What are the differences to traditional file systems? Virtual machines and microkernels, you might have noticed we're only discussing this on a relatively abstract level, just because each of these would actually be 1 semester of course in itself. Nevertheless, you should be able to define different sorts of kernels, so monolithic kernels, microkernels, hypervisors. You should know a bit about microkernels. So what problem did first generation microkernels have? How was this solved? What's an exokernel related to a microkernel? And then virtualization, what's it doing for the cloud? What's a virtual machine monitor or hypervisor? What's a type 1, 2 hypervisor? Which hardware support exists? What's paravirtualization? And related to this, what's a hypercall? So these are typical terms. So if you're ever going to work with virtual machines, you're going to hear them again. So it's good to know about them. Though, of course, we can't go into too much detail on this in the exam because we didn't go into too much detail in the lecture itself. So we went on with cloud. So we talked about service models for cloud systems. And again, this would be a complete 1 semester, of course, if you do it in an exhaustive way. We've looked at architectures for cloud OS. So of course, virtualization is one very important basic technology for a cloud OS. We've looked at containers, how containers are related to virtualization, what is virtualized in containers, so Docker, for example. And we especially looked at one performance critical problem, the virtual memory management, because essentially you have two levels of virtualization of memory now, one from the guest operating system to the view of memory the hypervisor provides, and one from the virtual memory view of the hypervisor to physical memory. And this is very inefficient if you always have to do two levels of lookup. So how can you optimize this? Can you describe this? And we also talked a bit about I/O virtualization approaches for the cloud. And finally, we talked a bit about OS security, and here only the first part, so lecture 21, I think it was, is important. So security and management, you should be able to define the terms security and also safety. You should be able to explain what the task of OS security is, maybe give example for malware. So what's a Trojan, what's a virus, for example. You should also know about different approaches to impact computer security, like what's social engineering compared to these types of malware. We already discussed this, and then we discussed like the basic ways for an operating system to ensure some sort of security. So permission management, related requirement, the principle of least privilege. How do we model permissions? Like we have the access matrix. And then we have different ways to use it, like file process attributes in Unix is one way to read the matrix. Access control lists, capabilities are other ways to read the matrix. And then also, how do the hardware and software interact for security? So what is the task of the MMU? And what is the task of CPU privilege levels related to security? We also talked about a bit about software-based protection. And we also talked very shortly about typical software bugs that can contribute to security problems, like a buffer overflow, which then goes back all the way to our start of the semester to C programming. And I guess that's all. Well, it's a lot. Yes, it's a whole semester it is stuffed. And this is still the basics of operating systems. So we haven't talked about how to implement a device driver. We haven't talked about how to implement a scheduler in detail. We haven't talked about how to implement an operating system. Essentially, if you're interested, then there's much more stuff to explore here. So here's a question. Do you have any tips for us when we now start practicing for the exam? Yeah, well, the usual tips you've probably heard many times. So go through the theoretical exercises again. Go through the example exam. I don't expect you to write large amounts of code, because writing code on paper is absolutely horrible, no matter if it's a text editor in a web page like on Inspera or a piece of paper. But I expect you to understand short amounts or short sequences of code, and maybe also usually I don't let you write long sequences or even short sequences of code, but there might be code, and you'll see some of this in the example exam, where there's just some stuff missing. So fill in something here, like fill in a semaphore call here. So these are very typical questions. And of course, all the algorithms, like scheduling algorithms, these are very important here. Other tips, well, does the exam assume that we have access to all resources? This is an open book exam. Yes, of course, you can and should have access to lecture slides, to your exercises, to your source code. Of course, the exam obviously assumes this. So in a home exam on Inspera, it's pretty much useless to just ask you to reproduce knowledge. So there won't be a question, describe the difference between a process and a program, because that's something you can just copy and paste from the slide. And I assume, yeah, well, that you know already how to do this. So it's more about applying your knowledge. So here's the problem. How can we solve this? And this is like the hands-on approach I try to do over the whole course. So yes, you should, and you're expected to have access to all the resources. And you can also use stuff you find on the internet. We can't avoid it anyways, right? So I'll take care not to ask questions which are answered on Stack Overflow. obviously, or only those where people make fun of students because they figured out, oh, that's a home that's a home exercise questions, and there's a lot of them on Stack Overflow. I can tell you. So no, I'm not that mean. So yes, feel free to do it, and yeah. What else can I tell you how to prepare for this? It's like for every exam, go through the slides, maybe use these questions in this set of slides to go through the slides to see if you can find the answers there. If you find the answers, you can start digging deeper from there. And of course, maybe you find interesting topics I forgot in these slides, but usually, of course, I'm using this set of slides here to prepare the set of questions for the exam. So essentially, I guess that's a good way to do it, starting from this slide set. And this is already uploaded on the net. And then going through all these details again and going through the example exam. I think that should help. Another question, if I haven't completed the theoretical exercises yet, are these a good way to practice? Yes, these are a very good way to practice for the exam, because obviously the theoretical exercises are relatively closely related to the types of questions that you can expect in the exam. I can show you the exam, but first I want to say thank you all for joining the course. Of course, most of you had to, but nevertheless, I had a lot of fun teaching that stuff. And if you're still interested in operating system topics, and I haven't managed to scare you off, I have officially started my new position at Bamberg University last Friday. So here's a nice picture of the old city hall of Bamberg, which is, I think, from the 13th century. It's on a little island and it's built in the middle of a river. So if you ever come to Germany, feel free to say hello, or if you want a student exchange, let me know and we can think about arranging some stuff. So yes, so officially I'm in Germany and sitting in my new office and waiting for things to fall into place. Another question, when do we start getting results for the practical exercise? So I checked yesterday, and I think practical exercise first should be graded. Espen, maybe, have you released the results yet? Because I haven't.
No, but I guess we will have to do a check of the TA's grading before we release, or
I looked through
okay.
through a number of these, and this looked fairly okay. But of course,
yeah. Okay. So if I wasn't aware,
200 submissions in detail. But I guess we can release them, and if there's any questions, the students can obviously
yeah, answer. I can release them right now, so that's no problem.
Okay. I think there was one late submission which was not yet graded. Well, we will have
no, that one is graded now. That one wasn't really late even, so
okay. I thought I'd seen. Okay, so the first ones will be available here, and I've seen that our TAs are already busy looking at number 2. So it'll take a while because we are not that many people, but we hope that we can also get the feedback on all of them. Yeah, probably before the exam, but also for number 3, but that will be a tight fit. So I can't promise this, but at least for the first 2, you know how many points you have. By the way, for the exam, you usually need about 40% to pass. So this was a question we had last year already, and of course that occurs in every course. Like, if I have all the points in the practical exercises, which count for 50% of your final grade, do I need to write the exam? Because you would have passed already. Yes, you do. And that's a formal requirement of NTNU because it's part of the exam. So the least thing you need to do is start the exam session in Inspera and hand in an empty exam. But obviously, even if you have 50%, this will not be a very good grade. So I would encourage you to still, definitely submit answers to the exam. Okay, thanks, Espen. So do you want me to go through some of the questions on the example exam, or do you want to have a look at this yourself? Give me some feedback on the chat. We still have some time left. Stop sharing that. Well, let's do a quick walkthrough. I need to be able to share that. Okay, running Zoom with 2 screens is really horrible. So that's the example exam and not the final one I'm showing you. Yes. Darn, right. So this is again on the wrong screen. Thank you, Apple. And now it has stopped sharing because I moved it to the other screen. All right, let's leave it at this screen. My goodness, this is horrible. So sorry for looking away from the camera, but I have to look at the other screen now. So these are example questions of the type you might expect in their final exam. So here we have put them in a nice form in LaTeX. Unfortunately, we have to put them in Spera, so they might not look as nice. But that's, yeah, well, life, I guess. So this is not only the type of questions, this is also about the number of questions. So you expect. So what you can do is you can go through the example exam and also time yourself to see if you have enough time. So if you're fast enough answering these questions. So we start off with a question about processes. So here, as I said, you're not expected to know all the details about C code, but of course you're expected to know about C programming. So we have pieces of C code, you should be able to read them, to understand them, and to answer questions about them. So here first we talk about process creation, and we always give the point. So usually I try to create tasks that are like 10 points each. So here I think we have 8 questions giving 10 points each. So it takes approximately the same time to achieve 1 point. Of course, you can't time it perfectly, but that's the way we're trying to do it. So the complexity of a task is related to the number of points you get. So if there's a task which only gives 1 point, don't spend half an hour on it because that's not worth it, obviously, and that's not expected. So here we have a typical task doing forks and more forks and even more forks. So here you have to build the process tree in your head and on a piece of paper, maybe. And the question is how many processes in total result from executing the code, including the process itself that we show here. Let's start at first, and you should be able to explain it. So which process forks which one? Maybe you can give example process IDs or something like this. A related task would be the second one, 1.2 here, about process execution order. So here the question is related, but a bit different. So process execution order in Unix is not defined. So if you fork a process, it's not defined if the parent or the child process runs next. So you don't have determinism here. So you should actually figure out which order, for example, outputs can appear on the terminal. And here you should really figure out which are the possible scheduling orders here and in which order something will be output. When we talk about system calls, we have a question about system calls. So for example, one question would be about a system call read. You all know this. Still, we explain what it's doing. And then a question about like the understanding. So this goes a bit to security. So which parameters do you get? Which parameters do you actually have to check in order to enable security? So to avoid that a user mode program can force the kernel to do operations that the kernel shouldn't do. And we talked about the Unix shell. So this task will be about internal and external commands. And here you're expected to, and if you implemented the shell, you should know this. So here's a relation again to the practical exercise. Here you're expected to actually explain if the change directory command can be implemented as an external command and work as expected. So really change the directory inside of the shell. If yes, explain it. If no, explain why not. We have typical synchronization questions here. So we here we have an example of a piece of code where you're expected to fill in missing things like essentially typical semaphore operations and also initial values of semaphores here. So essentially you're expected to fill in something at the commented parts here. As a question in between, can extra credit tasks compensate for points lost in another exercise? Yes, but I'm afraid not for points in the exam because of the 50-50 distribution we have to keep. So if you manage to have 120% because of extra points in the exercise, I'm afraid that's not possible because that would change the distribution of points to the exam. But you can make up for points lost in another exercise. We just sum them up in the practical exercises. So yes, so that would be a typical task, like really printing these prime numbers in order, and how can we enforce this when F1, F2, F3 are executed in parallel. We have some semaphore implementation questions. So here you should know about like atomic operations, for example, and you should also explain what a race condition is here for 3.3. And why this happens when you only have a simple instruction like x++. And of course, we have a question about deadlocks. So essentially, here's example code. The question is like, we have 3 threads here running in parallel. So 1, 2, 3. So we have initialization values from mutexes. And the question is like, can we have a deadlock here? And how could it occur? Or if not, explain why not. And then you could try to fix this somehow without leaving out important synchronization calls. So that's also a typical task here. And we have a task about memory allocation here. So the body algorithm, that's a typical task, you know, from a theoretical exercise. So you have an allocation order of 4 processes, and you should figure out like which pages of the memory are actually allocated to which process here, and also figure out if some allocation would be impossible because of, you know, power of 2 constraints and then just alignment constraints here. And we also have an LRU algorithm here with a reference sequence here. So that's something you should know pretty well on the theoretical exercises. You have 3 page frames. Yes, this is not very realistic, I know, but this makes it less complex. And then you should just give the, essentially the page frames, which are, the pages which are assigned to the page frames in physical memory, and then figure out which one is going to be replaced when a new request comes in. Then we have virtual memory, so you should be able to figure out translations on your own for segmentation and also for paging. So you're given a segment table and a page table, and you're giving 2 addresses, 2 virtual addresses, so segmented virtual address and paging virtual address, and you should figure out the physical address that results when you do the translation using the segment table or the page table. And there's another nice question about logical address structure. Let's see who can figure this out. That's interesting. That's an advanced question, to be honest. But this gives 2 points. So if you don't know the answer, it's not that critical. So don't spend too much time thinking about this, and don't write 2 pages about this, because that, isn't worth 2 points. That would be more. Of course, then we have scheduling algorithms. So we've all seen Gantt diagrams here, and we have different processes. So you should be able to, essentially show which process runs, which process is busy, which process is ready over time, with given arrival times, CPU and IO times. And we start by giving usually the first number of time steps here already, so you have a head start. We have a bit more about scheduling. So here you should look at different scheduling algorithms like shortest job first, preemptive round robin, and shortest remaining time first, and then figure out parameters. So you should be able to evaluate the algorithms here, and we give the formulas here, how they are defined with an example. So you should do the evaluation here for this set of processes. What else do we have? Of course, I/O, disk scheduling, and file systems, and that's already the last question. So we have something about file I/O and essentially what happens when we execute operations. So you should not only be able to read the C code here, but also to understand what the operating system is doing when you execute it, and then finally give the results. Yes, these types of questions might be a bit too easy, because you might be able to type them in and execute them. So we usually don't give the whole program. So you have something to think about. And then we have disk scheduling. And of course, the usual disk scheduling task is we have a number of requests coming in and a strategy like first in, first out, or elevator, or whatever you can imagine. And then you should give the order of tracks that are read for this given I/O scheduling. And finally, we have a question on file systems, so on inode-based file systems here. So here, that's an interesting question. So we have inodes with direct, single, and double indirect inodes, but no triple indirect inodes. And you should figure out with these parameters what is actually the maximum possible file size. And of course, just giving the answer, it's whatever, 42. Well, it's not 42, obviously. This is not. This is only a very small part of the answer. So here, when I have tasks like give the number something, calculate something, I need to see your calculation, because otherwise, well, it's just a result. And if it's wrong, we can't see where the wrong answer comes from. And that's all. I think that's not too much work. I'm not a friend of exams which stress you too much because you're running out of time. So you're forced to choose a subset of questions for which you don't know, like which are the easy ones, which are the difficult ones. So I'd rather love to give you time to go over your answers again, to think, to check for errors. And please, if you scan something and, handwritten, please ensure that your handwriting is readable, because otherwise we have really hard times. So I had a horrible example from last year. It was very unreadable handwriting, and it was written in English. Thank you. No. So please take care, or type it in and send a PDF. That's also fine. For PE1, why is the maximum score set to 10 points and not 16? Why did you expect it to be 16? Oh, 53. Yes, that's not exactly 16. So yes, that's 50%. So essentially we'll calculate the, 30 points in the end. So we have 10, 10, and 10 points for PE 1, 2, 3. To be honest, that is a result from last year, because last year we had 5 exercises, so it fit really well. So we have 50 points. So obviously, we'll map the 30 points to the 50% by multiplying them with the appropriate value. And then we are nice. We are rounding up just in case you're in between some points there. So yes, that was indeed the result of making life a bit easier for you by reducing the number of practical exercises, but keeping them at 10 points. Yes, and 16-point period 6 also would have worked. So I guess that's okay. And anyways, it's just linear transformation. Okay, maybe to get some feedback from you, and of course feel free to start to open your microphone. Is this an exam you expected? Would that be questions you think you would be able to answer right away? Or do you think, are you completely surprised, like, oh my God, I didn't expect any of this? And of course, after Easter, we'll discuss our solutions for the exam. So this will be another session. It won't be on Easter Monday, because Easter Monday is Easter Monday. So we'll probably have a slot on Wednesday then. Yes, you would have to double check the slides to make sure you had the allocation methods correct. That's okay. I also don't know all of them from the top of my head, so I'd also have to check some of those. But is there something completely unexpected, or rather what you think is what you expected? Yes, it's pretty similar to how the theoretical exercises were. Yes, that was the idea. I'm trying not to be unfair here by doing something completely unexpected. And this is like the fundamental knowledge you would be expected in like almost every operating system exam around the world. So I guess you should be fine with the exam. And of course, if there's questions during the exam, usually there's a phone number supplied, which will probably mean you'll have to call me in Germany. So that might be a bit more expensive, just in case there's really, really big problems and questions. But I think we only had one question in the exam last spring, and that was a misunderstanding. So yes. You think it's free to call the EU? Yeah. Well, it's right. You don't have to pay roaming costs when you're abroad, but you have to pay extra for calls to foreign countries, I think. But anyways, I mean, that's usually calling is for exceptional cases when something is really wrong or problematic. Otherwise, you're usually expected to assume something if something's not clear, and then add your assumption and we'll make the best of it. All right, so that's everything from my side. Thanks for joining the course. Thanks for all your interesting questions and comments on the forum. Of course, if you have questions about the exam, feel free to ask them on the forum. Questions about anything else, I'll try to have a closer look. Next week's will be a bit busy for me because I have to do my moving stuff from Scandinavia to Germany, and semester starts here on the 25th. And we'll have this new course on operating systems engineering. So but I'll definitely find some time to look into it, and of course our TAs will also take a look. So thank you again for joining the course. I hope I didn't deter you from looking at operating systems in more detail, and maybe see some of you in Germany in the future. Good luck with the exam, good luck with the rest of your studies, and we'll meet again, if you like, for the discussion of the solutions, but we'll also publish these solutions online, obviously, if you don't have time. We'll announce the exact time for this session because it's on the Wednesday, and then you'll have some time before the exam to prepare. Right. Thanks everyone. Thanks for all the fish. Oh no, that's the wrong book. And whatever. I hope you liked Unix a bit, and maybe some of you are convinced to use it in the future if you haven't done so already. Right? So Espen will be still available to answer questions about the practical exercise. And I'll stop recording now. I'll try to stop recording now. There. Yeah, Zoom has just moved everything to the right.